All right, welcome back. So we're continuing what we started in the last video where we began to apply the conservation of energy to a control volume in a fluid. And in doing that, we made some important assumptions that kind of helped us simplify the relationship. So one of the assumptions we made was that we were at steady state, so that there's no net energy change in the control volume with time. So these terms on the left-hand side of the energy balance go to zero. We also assumed that there was no mechanical work either done by the system on the surroundings or by the surroundings on the system, and we neglected any heat flow into or out of the system. So that left us only with terms dealing with energy transferred by the mass flow through the system boundaries. And so we broke that up into these four terms, and these represent kinetic energy, potential energy, and internal energy being carried through the system boundaries by the mass flow. And also this flow work term that represents changes in pressure and volume that accompany this flow of fluid into or out of the system. Okay, so now we can go through and try to obtain expressions for these individual terms in the equation. And let me just write them down here, and then we can talk about what they represent in detail. Okay, so the first term here represents the kinetic energy. So remember, kinetic energy is 1/2 mv squared, or since we're talking about rates per unit time, it's 1/2 m dot v squared. So the change, the inflow minus outflow of kinetic energy is 1/2 m dot in v in squared minus 1/2 m dot out v out squared. The next term represents the potential energy change. So that's associated with a change in height of the system. And so we can represent that as mgh or mgz, where z is the height. So per unit time, m dot in gz in minus m dot out gz out. Next we have the internal energy change terms. And so we have m dot in u in minus m dot out u out. And notice I've made this u with that little hat over it, and I'll explain that in a minute. And then the flow work terms, remember that's associated with changes in pressure and volume. So again, we have m dot in p in v in minus m dot out p out v out. Okay, so notice that the internal energy and the volume I drew with these little hats over it. And so that represents that they're specific quantities, or in other words, they're expressed on a per unit mass basis. And so this is, makes this consistent because we're multiplying by the mass flow rate here. So basically multiply by the mass and divide by the mass. So we're expressing volume per unit mass and internal energy per unit mass. So another assumption that we can make is that there's no accumulation of mass in the control volume. If we apply, conservation of mass at steady state, that supports this assumption. So basically what we can do then is say that the inflow mass flow rate is the outflow mass flow rate, and we can just represent that as m dot. And so here, remember, this is lowercase m. This is the mass flow rate, kilograms per second or something like that, as opposed to what I had on the previous slide where we represented the terms associated with the energy change of the mass flow by an uppercase m. Okay, so then I can just rearrange. I can factor the m dot out because it multiplies all the terms. And so then I have that the net energy change is the sum of the kinetic, potential, internal, and flow work terms. Okay, so let me rewrite this equation on the next slide. So again, we have the kinetic energy term, 1/2 v in squared minus v out squared, plus the potential energy change, g times z in minus z out, plus the internal energy change, u in minus u out, plus the flow work change, p in v in minus p out v out. Okay, so the next step is to recall that the volume, this specific volume, is volume per unit mass, right? Because that's how I defined it, volume per unit mass. And remember, density is mass per unit volume. So the specific volume is 1 over the density. Okay, another thing I can do is assume incompressible flow. So when I do that, I'm neglecting any changes in density. So I'm saying that the density remains constant. So now when I combine these two assumptions, I can write P in V in minus P out V out as P in over rho minus P out over rho. Right, so I can now replace this expression for the flow work with this P over rho term. Another important assumption that we're going to make goes back to this statement that there's small or no temperature changes that exist between the system and the surroundings. So remember, we use this to show that, or to argue that the energy change due to heat transfer was small and could be neglected. But this also has some implications with respect to the internal energy term in our energy balance. So remember, if we say that there's no temperature changes, or the temperature changes are very small, then the change in internal energy also will be small, because you can see that here in this expression, delta U is equal to mCV delta T. So for a small temperature change, this change in internal energy is also small and can be neglected. And so remember also that when we consider solids or incompressible liquids, which is what we're doing anyway in our development of this equation, that the specific heats at constant pressure and constant volume can be assumed to be equivalent. And again, I don't want to get too much into the thermodynamic details of these assumptions, but basically this assumption that we've already made regarding the fact that there's small or negligible temperature changes between the system and the surroundings allows us to neglect the internal energy terms or contributions in the energy balance. So when we do that, then we can simplify this further and rewrite our expression as follows. So we have P out minus P in over rho plus 1/2 V out squared minus V in squared plus G Z out minus Z in. So this equation then is referred to as Bernoulli's equation. So this is an expression for conservation of energy on the control volume in the fluid, but remember that it's subject to some important assumptions that I'm going to talk about in a minute. But subject to those assumptions, what we end up with is an expression that's very useful to help us solve problems in different kinds of flow situations. And again, we'll see that shortly. Okay, so let me just rewrite this equation here and we can discuss it a little bit more. So we have the change in the flow work, the change associated with kinetic energy, and the change associated with the potential energy on the system equals 0. And all these terms, remember, represent energy changes associated with flow through the system boundaries. So I can rewrite that in two equivalent ways that you may see also depending on what book you're reading or what papers you're reading. So delta P over rho plus 1/2 delta V squared plus G delta Z equals 0. Or P over rho plus 1/2 V squared plus GZ equals constant. These are all equivalent expressions for Bernoulli's equation. So at this point, I want to step back and remember the assumptions that we made when we developed these equations, because we made some very important assumptions, and these restrict the range over which these equations are valid. So first of all, we assumed the fluid was incompressible. We also made some assumptions that allowed us to neglect, or amounted to neglect, of viscous losses or energy losses due to viscous dissipation. And so for that reason, these equations are valid in the bulk flow away from walls or boundaries, and I'll talk about that more in a minute. And we also assumed that we were at steady state. So all these conditions have to be satisfied in order for us to be able to apply Bernoulli's equation to solve a problem. So this assumption regarding the viscous losses is important, and I just want to talk about that a little bit more here. So Bernoulli's equation is basically a special case of the conservation of energy that doesn't consider any losses or energy transfer associated with heat or work, because remember, we neglected those heat flow and mechanical work terms. So that's an important assumption, and as a result, it's really valid in the bulk flow. So by bulk flow, I mean away from boundaries, away from walls in the system, because at those locations is where we're going to have velocity gradients. And remember, velocity gradients are associated with stresses or frictional losses in the flow. So we would expect these kind of losses to be concentrated in these areas where we have these gradients. And so near boundaries is one area where we would expect to encounter these kinds of losses. And so as a result, we would expect that Bernoulli's equation would not be a valid description of the conservation of energy at those locations. Okay, let me just rewrite this form of Bernoulli's equation on the next slide because I just want to make one comment about another way you may see this written that's equivalent. So often in civil engineering and sometimes in mechanical engineering, it's convenient in terms of the kinds of problems that they solve in those disciplines to express this in a form where you basically divide each of these terms by g, the gravitational acceleration. And when you do that, you can see that each of these terms has units of length. If I divide g delta z by g, I just have delta z. And so these units of length are sometimes called head. And so if we rewrite Bernoulli's equation in this way, we have delta p over rho g plus delta v squared over 2g plus delta z equals 0. So this is known as the head form of Bernoulli's equation. And again, this is useful for solving problems in disciplines where it's convenient to have these energy changes associated with units of length or units of height. But it's exactly the same equation, it's just written in a different form.